In any event, the next speaker is Willis Eschenbach, who's I guess a Renaissance man. He has done many things. He is a climate researcher and an active and energetic blogger. And he even spent a little time working for the Peace Corps. Spent a little time in the South Pacific learning how to surf. So Willis could talk to you about a whole lot of experiences that he has, but today he's going to talk about clouds. And I told him that Roy Spencer set the table for him to discuss some of the things that are very important with regards to refining our understanding of the radiative effects of cloud cover. And he's going to talk a little bit about that.
Thank you. Okay, the usual puzzle. Press escape. My name is Willis Eschenbach, and unlike my other distinguished predecessors talking about science here, I have absolutely no credentials at all. I have no scientific education. On the credit side, I'm a self-taught climate researcher and amateur scientist, and I was the first person to file a Freedom of Information Act request with the CRU. And unlike many people that grew up on a cattle ranch, I am a reformed cowboy, although sometimes it's quite obvious that the reform didn't quite take. I'm going to talk today about the thunderstorm thermostat hypothesis, which is exemplified by this lovely thunderstorm over there. This is a supercell thunderstorm with an area that pokes up perhaps even into the stratosphere, a huge thunderstorm that's shown as seen from space. Let me start with a kind of a general overview of what I'm going to be presenting here. My hypothesis is that the temperature of the Earth is controlled generally by a combination of clouds and thunderstorms that keep it within a fairly narrow range. Let me look at a kind of a general overview of what I call the Great Hadley air conditioner and ice-making machine. This is the magic system that keeps our Earth from overheating. And the critical parts in terms of this discussion, the length of these arrows is proportional to the amount of sunlight that we get. And you can see that the majority of the sunlight is coming in here at the tropics. It heats the air in the tropics, and thunderstorms form and drive the air vertically around what's called the intertropical convergence zone, which is the area in between the northern circulation and the southern circulation. That rising air causes a huge cell of circulating air that rises and dries, comes out and descends in the great desert belts around the planet at about 30 degrees north and 30 degrees south. Now, there's a question about this that, in my opinion, doesn't get asked often enough. This is a hugely complex system with great circulating masses of air and clouds forming and coming and going and seasons coming and going. In any given spot, it varies by 20 degrees from day to night. And so the question that does not get asked enough, in my opinion, is, why is this system so stable? Yes, I know we argue about a half a degree in 100 years. And we dispute about a couple degrees over the Holocene 10,000-year period. But to me, that is an amazingly stable system. And the stability extends further into the past. This is a look at long-term climate stability. And the two heavy orange and blue lines are temperature records for the past half a billion years. Now, of course, these are estimates. They're our best guesses. One is by Scotese and one is by Jan Weiser. And there's a couple curious things about them. They appear to have a fixed maximum and a fixed minimum. and they only vary by about plus or minus 3%. Now, in a system that's somehow controlled by whatever changes are going on, a system where we have had meteors, giant meteors crash into the planet, we've had 1,000 years of volcanic eruptions, we've had continents moving from place to place. When the dust settles, there we are in the same narrow region. Even the fact that the sun has warmed over this period of time by an amount equivalent to that increase there, we don't see that reflected in the temperature record. And I'm a practical man who's dealt a lot with engines and machinery in my lifetime, and what that means to me is that this system has a governor. Now, a governor is different than simple negative feedback. Here's the governor system that most of us are probably most familiar with. This is the cruise control on a car, and you turn it on and it governs the speed of the car. Now, if there were no friction in a perfect universe, which of course we are very far from, if you put a force on the car, it's going to start going, and it's going to speed up and just continue to speed up. But in the real world, we have negative feedbacks, and for a car, those are friction. We get friction from the air that we're going through. We get friction from the rolling resistance of the tires. And so rather than increase indefinitely, we get a speed increase, and then at a certain point, it levels out. And this looks like a governed system, but it's not. If we come to a place where we start downhill, the car's going to speed up. And if we get a headwind, the car is going to slow down. There's no governor on that system. We're only looking at simple negative feedback. A governor generally controls the throttle, and that's what's happening in the car. The throttle in a car or in any system controls how much energy is entering that system. And by controlling the throttle, it can actually do something that looks more like this, where it drives it down below and up above, and it continues to oscillate around the desired value. To do that, it has to have a characteristic called overshoot. In a lagged system, that is to say a system where a forcing doesn't immediately make a change in some variable, there's a lag of time lag. To control a system like that, a governor has to be able to drive it back down below where it started so that it can oscillate around that value. And I will return to this question of overshoot here fairly quickly. About 7 years ago, I got interested in this question of why the Earth's temperature is so stable, and so I started looking for what kind of a governor the planet might have. I knew it had to be something that would control it over millions and millions of years. So I considered a whole variety of long-term processes. Things like the interaction, this gradual interaction between CO2 in the atmosphere making acid rain and thus controlling the or interacting with the carbonaceous rocks and forming a very slow, very gradual kind of control system. But I couldn't find anything that made any sense to me. And one day I had a curious insight, which was that if there were a system which was able to keep the Earth's temperature, or some portion of the Earth like the tropics temperature, within, let's say, plus or minus 5 degrees every day, that would keep it within plus or minus 5 degrees every year, and within plus or minus 5 degrees in 1,000,000 years. I realized that I'd been looking at the wrong end of the temporal spectrum, that what I needed to look at was short-term mechanisms that operated over hours or days. And I was living in the tropics at the time, and one day I was looking at the day and the way it developed, and I realized that I was looking at the governing mechanism. And we can see this mechanism in the tropical weather report. It's so common in the tropics that it's a cliche. At dawn, it's clear and calm. In the late morning, it clouds up, and within a fairly short time, it goes from clear skies to this lovely field of puffy blue, very innocent appearing clouds. They're not all that innocent, however, and in the afternoon, when the temperature reaches a new threshold, higher than the threshold necessary for cumulus cloud formation, some of those clouds go crazy and streak for the sky and become raging violent thunderstorms, which basically are only cumulus clouds on PCP. These raging thunderstorms typically increase during the afternoon as the increase of solar energy goes on. They die out at or around sunset. Sometimes they'll go on later into the night. And then we get progressive clearing until dawn. Now, how do these thunderstorms cool the surface? The clouds and the thunderstorms, the cumulus clouds and the thunderstorms, cool the surface initially through pure negative feedback. And that is the albedo. The albedo, as the temperature rises, cuts down the amount of energy entering the system in the way that you would expect. However, it's not enough to slow the rise of the temperature. So what happens is that as the temperature rises, thunderclouds form. And they have a host of ways that cool the surface. The first way is that they dodge the CO2. They form what's essentially a wormhole between the surface up to the top of the troposphere, where huge amounts of warm air are taken up and move up to the tropospheric level inside in this enveloping cloud area that we see in the middle of this thunderstorm here. And in there, they're shielded from interaction with the greenhouse gases. There's no thermal radiation interaction. There's no turbulent interaction with the lower regions of the troposphere. They're hidden from view until they come out and emerge way up at the top, where there's very little water vapor, there's much less depth of greenhouse gases, and they are free to radiate their energy out to space. Thunderstorms also cool the surface by wind-driven evaporation. The winds at the base of the thunderstorm cause evaporation, which cools the surface directly. Over the oceans, which are, as you know, some 3/4 of the planet, they increase the albedo by increasing the amount of breaking waves and spray, white foam. That white foam reflects the sunlight and reduces the amount of energy that's going into the ocean. They cool through cold rain and cold wind. When the rain falls from the cold heights, it entrains a wind, and when it comes down, it blows out in all directions at the base and cools the surface. We know from the second law of thermodynamics that heat only runs from warm areas to cooler areas. But thunderstorms kind of stand that on their head with one of nature's most amazing tricks. Rather than moving the heat from the warm area to the cool area, they take chunks of cold in the form of snow and hail and cold rain, and they move the cold from the cold areas to the warm areas. It's quite astounding to me. We also get increased cloud reflective area from thunderstorms because they not only reflect off the top like the cumulus clouds do, they have this huge reflective area on the side. And particularly in the afternoons, that reflective area shadows a very large amount of the surface. They cool through modification of upper level clouds and the changes in radiation discussed by Professor Lindzen and Professor Spencer. They also lead to enhanced nighttime radiation because the clouds die away at night. So it's clear during part of the night and free to radiate to space. Finally, they deliver dry air to the surface. This pillar of rising warm air has the moisture stripped out of it, comes out at the top, and descends in a circle all around each thunderstorm, and it's dry, and so it lacks the major greenhouse gas, water vapor, which leaves the surrounding areas free to radiate up to the sky. When I realized all of this, I thought, oh, good, I'm on to something now. But what I didn't have was any idea of how globally the mechanism operated. I could see it day to day, but it was different in the morning than it was in the afternoon, and disappeared entirely at night. And it was different in the seasons, which you have even in the tropics. So I wanted a point of view where I could look at this system without all these distractions. And one day I realized that there actually was such a point of view, and that is the point of view of the sun. When we look at the Earth from the sun, there's no nighttime at all. Everything you can see is daytime. And there's no summers and winters. It's always summer under the sun. And if we take the usual convention of north being up, the Earth rotates as seen from the sun in that direction. So this here is dawn. And over there we have sunset, and the line down the middle is noon. And each of these represents different times of the day. So what we've done is we've traded a temporal dimensions for spatial dimensions so that we can see what happens. And what I found, this is the average of a year's worth of photographs from the GOES West satellite to show on average what's happening. And here in this box around the intertropical convergence zone, we see that in the morning, the albedo is running at about 30%, and between about 10:30 to 11:30, it takes a very quick jump up to about 34% and stays in that area with increasing variation during the day. And the other day I saw a cloud model, a superparameterization model, which showed exactly that pattern. This results in a change in the incoming solar radiation, which is a drop on the order of about 60 watts per square meter in the course of about an hour. And we can compare that to the 3.7 watts per square meter from a doubling of CO2. So I did this as, in a sense, a hypothesis test of my hypothesis, and I found out that, yes, in fact, this is the way that this is operating in the tropics, that the albedo is keeping the incoming energy down. But this is not the governor. This is just the albedo, the negative feedback. So how does a thunderstorm operate as a governor with overshoot? The key to understanding that is that thunderstorms are a dual-fueled heat engine. They're a heat engine that translates energy, heat energy, thermal energy, into mechanical motion. And they run off the fact that when you have low-density air, that air starts to rise, and if enough of it starts to rise, a thunderstorm is created. Now, there's two ways to get low-density air. You can get it through adding heat to a parcel of air, or you can get it by adding water vapor to a parcel of air. And wind drives the evaporation under the thunderstorm. Evaporation basically rises linearly in general with wind, so if wind doubles, we get double the evaporation. Over the ocean, we also get spray, and the spray goes up into the warmer air and evaporates much more quickly. It also vastly increases the surface area that's evaporating. And finally, we know the shortest distance between 2 points is a straight line. When the wind creates waves in the water, we get a larger surface area. So this wind, which is created by the thunderstorms, is generating its own fuel. We need a certain temperature to initiate the thunderstorm. But once that thunderstorm is initiated, we get winds that, for example, here's a day's worth of wind, or a couple days. It's running about 4 or 5 meters per second until the thunderstorms come by, then it's peaking at 24 meters per second. So we get a huge 8 to 10-fold increase in evaporation, which is creating new fuel, and that allows the thunderstorm, which might have an initiation temperature of, let's say, 25 C, to keep running even though it's getting cooling the surface all the way down to 21 or 22 degrees C. And this provides the overshoot necessary for a functional governing mechanism. Now, there's been people who've said that the causation goes the other way. The climate models say that the cloud feedback is positive rather than negative, as I'm saying. And we can show that that's not the case by looking at the model of tropical albedo. This is from the ERBE data, and it shows how the tropical albedo changes with the seasons. And you'll notice that in the summer in the northern hemisphere, in August, we get heavy albedo up in this area up in here in August. It moves up into northern South America and the Sahel region. On the other hand, when the sun runs down to the south, we get high albedo in Brazil and in South Africa. And unless we want to believe that the movement of the clouds is what governs the cyclical movement of the sun, we'd have to say that the temperature is driving the clouds and not the other way around. So in conclusion, thank you. In conclusion, let me say the takeaway point in this is that this governing mechanism, the operating temperature of it, is set by the physics of winds and water. It is not set by the forcings, and that as the forcing of the sun increases, as the forcing of CO2 increases, it doesn't matter. The governor is set to a temperature which is not run by CO2. It is governed by the inevitable and unchanging rules of the physics of the wind, the waves, and the ocean.
Bravo.